Hi, my name is Jason. I'm from York University, Canada, and I'll be presenting our work on long-term photometric consistent null view synthesis with diffusion models. Given a single image that was captured from the starting perspective in the scene shown right here, can we predict what that scene looks like from other perspectives along a trajectory? Null view synthesis is a problem that is well suited for generative modeling due to large amounts of uncertainty. In this example, we are given an image of a simple scene, shown on the left, captured from this camera pose here. If we view the scene from a new perspective on the right, there may be many plausible images for how the scene may appear. These uncertainties can be due to factors such as occlusions, or unobserved regions outside the view of the source image. To generate a trajectory of null views, we sample the views autoregressively. This means we model the distribution over each null view by only conditioning on the most recently generated view and the relative camera pose. For example, given x0, we condition on it to sample x1, and we condition on x1 to generate x2, and so on, until all views have been sampled. We learn the distribution of null views using a two-stream diffusion model, where one stream processes the source image, and the other stream processes the noisy intermediate images of the null view. The weights are shared across the streams while only communicating using cross-attention layers, which are modulated with relative camera pose information. Standard metrics for null view synthesis do not directly measure the consistency of the generated views with the desired camera motion. We propose thresholded symmetric epipolar distance, or TSED, a new consistency metric where the core idea is to measure the consistency of the two images using a set of point correspondences, and the epipolar geometry of the camera poses. Specifically, for a pair of correspondences across two views, each point induces a line on the opposite image. When the views are consistent with the view geometry, the points ideally lie on the epipolar lines. If the views are not consistent, then there will be large distances between the points and the epipolar lines of each image. For evaluation, we use two standard datasets, Real Estate 10K, shown on the left, which consists of real estate tour videos scraped from YouTube, and Matterport 3D, shown on the right, which is comprised of rendered meshes that are reconstructed from scans of real indoor environments. We evaluate generated sequences using trajectories from the datasets. We also generate sequences over custom trajectories. The specific trajectory shown here is the hop motion, where the camera moves along a vertical semicircular path while pointing at the center of the scene. In the middle, we have a generated sequence with the hop motion shown here. On the right, we have a visualization of the camera motion. In total, we define 3 custom trajectories: hop, orbit, and spin. The ground truth trajectories serve as in-distribution camera motions, while the custom trajectories are used to evaluate the model's ability to generalize to out-of-distribution trajectories. Using our metric, we show that our method is more consistent than the baselines, especially on the out-of-distribution trajectories, which can be observed qualitatively in this example with the hop motion here. Additional qualitative results can be interactively viewed on our project page, accessible with the information on the top right. And check out our paper for more details.